So this R will be our discussion in a few subtopics, which we are going to see later on. So basically what this says is if we have an exponent, we are going to have some sort of convergence and divergence with different R. Okay, with different R, we can have some variation. And if we would like to know like how this R could be converged, it can be converged, for example, it can be 1 or it can be 0, for sure. And then we are interested on finding in the number in between, the fractions, the positive fractions, negative fractions, and we could have this different numbers. Okay? And you see that we can have a convergent here, a divergent over there, right? And say here we can have a convergent and divergent over here. And yeah, that's the R with power of n. Okay, so let's go for the next one. So the next topic is about the monotonic and bounded sequences. Oh, it's happening again. Okay, no. Okay, so the the definition we see from this theorem that the sequence will increase if the number or the terms is less than the next term. So the previous term is less than the next term. Okay, that we say that it will be increasing. And then it will be decreasing if it is going to be the previous term is greater than the next term. Okay, I think that is mathematically can be understood. Okay? But this is going to be important if you want to prove the sequence increasing or decreasing. So we can prove that by taking into this to definition whether the sequence increase or decrease. Well, basically, you can prove through that, or you could just check by some number, and then you could try and then see whether the number becomes increase or it decrease. Okay, so you see that is how we can say either increasing or decreasing. We call whether it is decreasing or it is increasing, that sequence will be, we call monotonic. So it cannot be both. Okay? So it's mono, one. So it could increase or decrease. That's the first thing. So that's a monotonic sequence. So if we have a sequence, let's say the sequence is n over n squared plus 1. So if we want to know whether this is decreasing or increasing, and perhaps if we take some number, let's say 1 and 2, we see that it seems that it is going to decrease. So what can we do in mathematics is we could show that show an is greater than an plus 1. And basically that is what we are going to do. So we just take the expression and then substitute with the n plus 1. And then check whether they are correct. So we can cross multiply. Okay, so here we have n, and then this will be n plus 1 squared plus 1. And then here is
going to be n plus 1 multiply the n squared plus 1. Well, I think we can just take the multiplication to see how it looks like. So this will be n squared plus 2n plus 2. So we can multiply n cubed plus 2n squared and then plus 2n. And then this is going to be greater than the n cubed plus n squared plus n plus 1. And then solve. This one cancel. And that one become n squared plus n. And for sure that if for n less or greater equal 1, this is true. So true for this. Okay. So at the end we need to write the conclusion. Okay, to write the conclusions, and I think this will be very important in chapter 11. Write a conclusion that since an is greater than n plus 1, then an is decreasing. Okay. Oh, okay. Still vulnerable. In other classroom, it's fine. No problem in the HDMI. So that's monotonic, okay? Monotonic. Increasing or decreasing, that's monotonic. It's a little bit different from the sequence that has oscillation. For example, we can have like oscillation and then finally arrive at one certain point. It's a little bit different. So another thing, aside from monotonic, I will just zoom a little bit here. There is a second definition, which is about the bounded sequence. So a sequence can be bounded above if there is a number m. So let's say m is a number that is above, that the sequence always below this m. Okay, so it will not precede the m. So m is like the upper level, like this, like m is over there, and we are below, okay, or maybe the same height as m. And then there is a sequence called bounded below. If there is another m, small m, that is m is always less than the sequence. So it's going to be the floor. Okay, like in the floor now, m, the small m and it's big m. And we call it bounded below. And this definition will be we call this as bounded sequence. Okay? So you see, you have monotonic and you have bounded. So if you have a monotonic sequence, either increasing or decreasing, and it is bounded, it will be a convergent. It will be convergent. It will be convergent. So if you have, like, for example, it's increased, and then suddenly there is some number that is always up there, and it will not getting crossed. Okay? It will not proceed that number. So we say that it will be bounded to that number. Okay? So we say that is converge. So the sequence converge. maybe just an illustration here. Let me just take a zoom out a little bit. Like this one here is increasing, monotonic, but then it's bounded here, which we say that, okay, as we increase the sequence, maybe sequence at n equal 100, it is getting really, really close. And because you say this will be converged to this value L. Okay.
What is the difference between this number and limit?
I think limit is a tools to say, and this is just an illustration for the definition. Okay. I think very similar, very similar. I could say. Because at the end of the day, we will use limit for our tools. Okay. And I think to prove also, we can use limit to prove this. I use precise definition limit. I think the same. This is just a to define what is monotonic and what is bounded. Okay. Okay, I forgot to write here the conclusions is number 12. So every bounded monotonic sequence is convergent. So sequence that is increasing and bounded above, this will be converges, and sequence that is decreasing and bounded below. Converges. And there are several proof and some additional axiom to explain this, but I think I should continue for a while. So I leave the proof and axiom later on. If we have time, we can go back and explain on some proof here. But I think the proof is basically we can use the precise definition of limit, which we include the epsilon as a small distance between the L and the L plus epsilon and L minus epsilon. Okay, but I think we don't have time for that. So I will leave the proof later on. So that is actually the sequence. Okay. The next subtopics will be further studies of sequence, which we are going to see a series. Okay. So we are going to not only look at the list of numbers, but we see the sum of the sequence or sum of the list of the orders. Okay. Now let's go for the series. Okay, as we mentioned at the early introduction of sequence, we have these conditions which we call the Zeno paradox. You could look up that paradoxes that is situated by Zeno, and he stated on how could be ridiculous. But then, if we want to compute the total distance this man walks, and if we increase the number n, then we can express the sum of infinitely many smaller distance as this one. So for example, if this is 1 meter, then we say that it's half plus 1 over 4 plus 1 over 8 plus 1 over 16 plus blah 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 as the n increase. Okay? And of course, if we see this, and we could imagine the real numbers that we point into the calculations, and we use calculate maybe n up until 100, 1000, we could get number around 0.999 something, that we argue that it will be closer to 1 in limit. Okay, so we say that although the Zeno, he still argue that it doesn't make sense to add these infinitely many numbers together. But there are other situations that we can see from decimal notations. Okay, so decimal notations. If we see decimal notation, for example, a p, okay, pi. If we could break down the number of pi, we see here the number of pi. The convention, the official number is this, okay? And still there remain many numbers behind, which they are still mystery. But if we try to break down all this component with each of the point decimal, we could get this. And we could see that if we add more terms, the closer we are going to get the real pi number, okay, if we add this. Okay. So this is just an illustration on how taking the sum of the infinite sum will have some unique conclusion that we are going to discuss. So we are going to learn what we call as the series, or here is the another term, infinite series. So it's similar to sequence, how we write. If we add terms of infinite sequence, this is sequence, we usually write this from n equal 1. We are going to get expressions a1 plus a2 plus a3 plus an, but it doesn't end, right? It doesn't end. We could get n plus 1, n plus 2, n plus 3, right? So it could take, let's take forever. So a1 and until we don't know how much, right? So there must be some clear analytical or observation that we need to do to break down what is happening in the series. Okay. We could write this for the infinite series. We usually write in terms of the sigma of the an. An itself is sequence, okay? Or simply just sigma an. That is pretty much the series. Okay, so for our discussion, this could mean something, but still it is not easy to follow. If we, for example, we start by taking like 1 plus 2 plus 3 plus 4 plus 5 plus we don't know until when, it would be like really large and we couldn't control, right? We cannot control. It will be really large. But if we start talking from the Zeno, the previous paradoxes, we start by taking half plus 1 over 4 plus 1 over 8 and etc. We could see something. Okay, we could see something. So if we add, let me write here. So if we add here, so here if we add, just take the numbers, half plus 1 over 4 if we take terms and we increase the terms, the sum of the first n terms, so if we take n equal 1, okay, this is just 1 over 2, n equal to means a1 plus a2. Okay, let me take closer and let me write what does that mean. Okay, so this means this one is a1, this one is a1 plus a2, this one is a1 plus a2 plus a3 and etc. Okay, we call this is the sum of the first n terms. And if we see the result, we could see that somehow it will be near 1 or close to 1, right? It will be close to 1. It seems reasonable, right? So let's say here, it's reasonable to say that the sum of the 1 over 2 power n is getting closer to 1. Okay. Now this idea for this a1 plus a2, a1 plus a2 plus a3, this could become our new sequence itself that we are going to use to break down the series. Okay. So I will write a1 becomes s1. So I will write here, this become S1, this become S2, this become S3. So S is the partial sums. So this is the idea of, we call the partial sums. So we are going to to, to, to elaborate the infinite series in a fraction by fractions by fractions. So we are going to have A1 as S1. We have A1 plus A2 as S2. A1 plus A2 plus A3 as S3. And we are going to see this as a new sequence. As a new sequence. So we're going to have the Sn will be equal to A1 plus A2 plus dot 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 plus An. Or we say the Sn equal to sigma start from I equal 1 until n Ai. So this will form new, let me write with the red. So this is a new sequence, which we will have, maybe we see the limit or maybe not. If this exists, limit exists, then we call this is the sum. We can count the sum if limit exists. Okay. The limit as in what we've done in sequence. So the official definition here, let me just wrap up what we have above. So let me just go through the definition first, and we see how we could elaborate. So if we have a series, A1 plus A2 plus A3, etc., and if we define the partial sum Sn as the sum of the Ai, or the terms in sequence, so we are going to add this A1, A2, A3, and etc. until An. Now we have an ending. If we just adding this, we don't know for how long. But if we split and make it into partial sum, the partial sum itself is a sequence that can be having an endpoint here. Okay, so it's easier to see and it's easier to follow for finding whether this will be a convergent phenomenon or not. Okay, if the sequence Sn convergent and the limit exists as a real number, we could find the value, then the series will be convergent. And we can write as A plus A2 plus blah 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 as equal S, or the sigma An equal S. Now this is what we call the sum of the series. The sum of the series. And if the sequence of the Sn diverge, then we call the series is divergent. Okay. Now since we are going to find the series, whether the series is convergent or divergent, there will be several methods, several techniques, at least 8 or 9, which we are going to apply to prove that it will be convergent or not. So it doesn't simply work like a sequence before, which we can try to use limit and we find the sequence converge or diverge. Now we need to use different things, and because now we are going to sum up all the sequence. And by the series here, I hope the next time we see the problem in sequence and series, we know which one is sequence, which one is series. If we mix up both between both of them, we are going to have a mix up definitions. I will tell you later what is going on. Okay, so let me go through. Okay, now let's have some small example just to see what will be. So suppose we know that the sum of the first n terms of the series is, so we know the Sn, okay? We know the Sn, so the sum for the n, for the an itself is the limit of the Sn. Okay? Now because we are given, okay, this is given Sn, so we could just take the limit, and then taking the limit of this partial sum, and basically we see that we can just write 2/3, right? Agree? Right? Now of course this is if this is a Sn. But most of the time, if you see the next examples, like we are going to have some practices later, we usually given the sequence, not the Sn. So that means it is not works like this. This is if this is an Sn, then we can take the limit directly. Because we are using the new sequence Sn, and we take the limit. Okay? Just like a normal sequence. But later, usually we are going to be provided only the sequence, which is different from the Sn. Okay? Okay, now another example here. So we have the series, sum of this. So now this is not Sn, this is a sequence. So perhaps to get to the inside this summation, if you perhaps try n equal 1, try n equal 1, try n equal 2, n equal 3. So if we say, let's say we try n equal 1, we see that this will be 1/2. When we have n equal 2, this will be 1/3. So let's just break down for a while what we have here. So let's write the partial sum. So partial sums, oh, it's gone. Partial sums Sn is going to be defined as, and here we can just substitute the n with, let's say we start by we change the n with I just for this calculations. So we can see that we could write 1 multiplied by 2, and then plus 2 by 3, right? And we have an ending up until here. Okay, now it seems that we have a quite a pattern. 1, 2, 2, 2, 3, 3, 4, 4, 5, 5, 6, and so on and so forth. And we have to have that some kind of pattern. And then we have this fraction, which if you still remember, in calculus 1 we did partial fractions. It's familiar with it? Oh, I think I know. Still remember? Okay, so if we take the partial fraction of this, we split this into separate fractions, we are going to get, let me just write here and take as partial fractions. And we can write the, let me just write with green, 1 over, this will be 1 over I minus 1 over I plus 1. Okay. Okay. If you want to know how to do it, look back the notes last semester. So we could separate this, become 1 over I minus 1 over I plus 1. Which if we try to take the number back into this one, so now each component of this become this separate. And then we take 1, 2, 3, 4, and so forth. So this will be 1 minus 1 over 2. So let's write here. Let's write again that this Sn it will be, I think we can just write 1 over I with a bracket. Okay, I think we can have a break. We can continue later. So okay, let's continue this part. Okay. So now we input the number, the terms, from 1, 2, 3, 4. So for 1, this will be 1 minus 1 over 2, and then plus. This is I equal 1. Okay. And then I equal 2, this will be 1 over 2 minus 1 over 3. And then plus, this is 1 over 3 minus 1 over 4. Okay. And plus, this will be another 1 over 4 minus 1 over 5. And you can see that it will reverse every time we increase the terms. We are going to see the patterns. Okay? So I will just end, and then we go for the last terms that we might have. So the last term will be the end. Okay. So this is when the I is equal to n. Now, the terms now, it could canceling in between. So we see this negative 1 over 2, plus 1 over 2, we can cancel this, we can cancel this, okay, and so on and so forth. So we could cancel everything in between. Okay. So we could cancel this, and this, and also we are going to expect that this 1 over 5 also cancel, right? With somewhere there, and this 1 over n will also cancel. So at the end of the day, we could simplify our Sn and taking into 1 minus 1 over n plus 1. And how about whether it's converged or not? Then we take the limit of this Sn. So we take the limit Sn approaching infinity of this Sn. and we get that this will be 1, right? Since the limit of the 1 over n plus 1 will be 0. Therefore, we can say that the sum of 1 over n plus 1 is equal 1, and therefore series is convergent. This we call, the techniques for this one we call, the whole thing here, what we did with the cancelling, we call this is the telescoping sum. So why it's called telescoping sum? Like if you see movies or maybe cartoons that has a pirate, usually they have a telescope that you can pull, and then they will extend, and then see. And telescoping sum means we pull the telescope and whoop, we squish, so we squish this like a telescope. So that's why the name is telescoping sum. Okay, and the interesting for the this Sn and how it differs from the normal sequence An is, if we could see here, let me just zoom out and take this in the front here. If you imagine only the An, if we have the An, for example, our An is 1 over, let me write there. So An, the An is 1 over 1 over n plus 1. And Sn is 1 minus 1 over n plus 1. Okay. Now, because of this nature, 1 over n plus 1, if we take limit, this will be 0, right? This will be 0. 1 over something big, infinity, it will be 0. So it will be going there. Okay, it's converged, but it's 0. If you have the Sn, we're going to have this 1, which we have on that red dots. This is how it could differ. And in the other cases, we could have that is if the sequence could be converged, but the Sn might diverge. We can have something like that also. So you need to be careful to define something when you are given a problem. You need to know which one is the sequence and which one is the series. So if you are given, for example, the sum, and then you are given like a function inside those sum, and we could see that, okay, that will be supposed to be a series that which perhaps we want to make a statement whether it is converged or diverged. Okay. Okay, let's continue a little bit. So I will review again later, okay, with some examples, but I think I will continue a little bit for the introductory of series and some of the techniques. So let me go for another subtopic of the series is the geometric series, okay? The sum of the geometric series. So geometric series, as you may heard perhaps before in previous lecture or courses, that is a series which we are going to have the ratio, and we have the r. Okay. So basically the series would work with, if we multiply the first term with the r, and we get the second term, and we multiply the r, and multiply again, and we will have some list of numbers. Okay, that is the geometric series. So let me write here. So each term obtained by multiplying r, okay, or ratio, or common ratio. The series that we discussed before, the Zeno, the 1/2, that is the series when the first term and the ratio, they are the same, 1/2. So 1/2 multiplied with 1/2, and etc. and so forth. And if you see, if we take r equal 1 for all the list of numbers, then we are going to have the Sn, it becomes a plus a plus a until some number a at the end, and we could just write down na. And if we have n larger, then limit will not exist, right? Let me just write the ne, okay? It doesn't exist. So this will diverge for r equal 1. So we need to define again a new r which works with this series. Okay? So it will work if we have r is not equal 1. So we could write the Sn as a plus ar plus ar squared plus dot 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 ar n minus 1. Okay, now to make it, or to simplify this before we arrive at this, so to get the result, or what is the best practical approach to know the formulation of the sum for this geometric series, I think, if I'm not mistaken, this is solved first by Gauss, the same guy who, I don't know, you learn Gauss elimination method or Gauss distribution? Not yet, right? Okay, so the same Gauss, he discovered when he's still in elementary school, which I also surprised. So what he did, so he multiplied all of this with another r. Okay, so he multiplied with another r. So I will write that as a second equation. Okay, so he write and multiply. This will be r Sn, and I will write the first term here just to see that it will be coincide, and this will be pi cube, and we are going to have this, and also the last term which we multiply with r, this will be a r with power of n. And then he is going to subtract this. So he subtracted this term, all of it, which we have now, Sn minus r Sn equal, so we have a here, so we write it a, and all of the terms in between will be cancelled, right? It will be cancelled. So we could just write the last terms, which is minus a r with power of n. And with simple simplifications, we have Sn 1 minus r, right, equal a 1 minus r with power of n. And we get that this will be a remember, this is works with r is not 1, or from the previous, the sequence I mentioned, that if -1 less r less 1, so r with power of n will be 0 as n is larger. Okay, wait. Okay, so that is the formulations for the Sn for geometric series. Okay, now we'll write for a while here that if we take limit, so we write here, so the limit of the Sn is the limit of all of this. So since r with power of n will be 0, so we could just write that we are going to have a over 1 minus r, or let me write here, and it's multiplied with a and multiply with the limit of the Rn. So it's simply, I've just factorized the a over 1 minus r. And since this part will be 0, so we're going to have that the limit is a over 1 minus r. So at the end of the day, when r in absolute value less than 1, geometric series, it will be convergent. The sum will be equal to Sn equal a over 1 minus r, which I think probably you have seen somewhere, I think in your maybe school. Let me just give you this, okay, this part here. And uniquely, if you see how the geometric series could be also understood from geometric, okay, so that's how it came, the name. So we could imagine that we have suppose we have a rectangular shape or square with the sides equal a, okay. And then we multiply that a with r. Of course the r should be the ratio should be in fractions. So we expect that it could be this AR, and the same thing, this is should be the another square, and then we multiply with r, then we have this IR squared, and we have this whole triangle. Okay? With the base will be AR squared, and so on and so forth. Okay? Now the S, okay, is basically the sum of all the sides. A plus AR plus AR squared plus etc. Okay? Now the deal with this is, since we take this in triangle, so by taking ratio of the triangle, then we could write this as the S over A should be equal to A over A minus AR. Okay, so S over A, and then this A over A minus AR. They are similar triangle, right? They are similar triangle in general. So, solving this, then we say that we have as the same formulations. I think historically it came from this geometric problem, and then they make a series. Okay. Okay, so I think for next week we can have a review and some exercises. Have I put some exercise? Not yet. Okay. I will try to put some exercise for you this week, and we can discuss next Tuesday. And Thursday we'll have quiz 1 hour, and 1 hour will be class. Do you want to be the first hour or the second hour for the quiz? Because of the first hour you will not be, you are not going to have a focus. You will feel nervous. Okay, so just a quick note and example. Okay, just a quick note. So if we have given this kind of series, okay, I think this is quite simple, right? So if we see this series, and if you want to find the sum of the geometric series, first we need to know what is the term. Okay, what is the term? The term is the A is 5, right? And what is the ratio? The ratio is if we see how it could derive all the numbers, it came from if we multiply with -2/3, right? So we see that this R is -2/3. We need to multiply this to get all the list of numbers. So we know that the R is less than 1, right? Or I mean, right, R is 2/3 and it is less than 1. So the series should be converged. Okay? We could just immediately take that action, and if we need to find the sum, then since series converges, my writing is so bad. Then the sum is 5, 1 minus 2/3. So 5/3. So 3. And statistically, or in enumerations, if we are trying to compute one by one for the Sn, we could see that the Sn, the partial sums, if we increase the n from 1, 2, 3 until 10, we could see that at the beginning it doesn't seem to be converged, like 5, 1.6, 3.8, and as you increase 2.4, 3.3, you will see that it is going to be getting closer and closer to 3.17, 2.88, 3.07, and we will get closer to 3, which we could see that it is perhaps the behavior seems to be getting converged. Okay. So that is actually since I'm allowing you to get a calculator, you could predict and assume and try some numbers if you want. Okay. Just to check, immediately check. But what I want is, what you need to write is some proving needed for the basis, the mathematical concept. So that is just my suggestion. So you could just go immediately check with your calculator, okay, if you want to know like whether this will be converged or diverged. I think you can type for long sequences or series, right? And you can see how it works. Or, as I defined, as we see the definition, we could work out the Sn. You can see the Sn. 1, 2, 3, you check. So this will be A1, this A1 plus A2, A1, A2, A3, A1, A2, A3, A4, and so on and so forth. So you could see and compare from one to another using your calculator. So that is one suggestion that you can take if you are maybe not having any clue how to do it at the beginning. You could check first, and then later you need to figure out officially using mathematical concept or calculus. Okay. And I think this is the graph. Okay. As for the table, okay, and we see that it will be closer to 3 converges. Okay, now see another example. So for geometric series, aside from you are giving some list of summations, and you need to define or maybe identify whether it is geometric series or not. The second thing is you are given a series like this. Okay, you are given a series like this. And then perhaps the question is just asking whether it's converged or diverged. Okay. First thing, like I said, you could try this just to see maybe some numbers. Maybe you can try n1 to 5 or 6 just to see whether it is going to oscillate and closer to something, or you can see that the number is actually uncontrolled, so it's going to be like large or maybe negatively large. Okay. But for something like this, since we are still in geometry, we could try some sort of algebraic manipulation to see that if this is going to be equally the same with our geometric formula. Okay? So we need to make the form of, so geometric series form is AR n minus 1, right? Or the sum of AR n minus 1. So you need to be observant. So you need to be careful here. And maybe we take only the formula here. Okay, so let me just write. So what we can do, so first perhaps we could make this 2 with power of 2 and then n. And then maybe I will make this n minus 1 since it's supposed to be n minus 1 for the ratio. So let me just write here minus n minus 1. Since 2 with power of 2 is just a constant 4, so let me just write 4 to make it easy. So 4 with power of n. And then 3 with power minus n minus 1. I will write this as, because negative, if you have negative 1, it's supposed to be you are having a fractions. So 2 with power of negative 1 is 1 over 2. So with this 3, we are going to have 1 over 3. So I'll write 1 over 3 n minus 1. Or we could write 4 with power of n. So I will write slowly here. This will be, or maybe just write 3 n minus 1. And I could rewrite this. I would like to rewrite this. Since both has the n, so I will write this as 3 over n and then 3 minus 1. Okay. So since we have the power of n, I would like to write in n minus 1. So I need to multiply with 4 and then write as 4 over 3 and then n minus 1. So we are going to have the A is 4 and the R is 4 over 3. And since the R, so since R is 4 over 3 and it is greater than 1, then the series diverges. And like I said, we can have some identifications through checking with the numbers n. So checking n equal 1, 2, 3, maybe until 4. So checking 1, so we get the A1 is 4, right? So A2 is, it's 16 over 3, right? And A3 will be 264, right? 64 over 9, right? And so on and so forth. And we see that it's also it also can be proved from this part that we could identify that the A is 4 and the R is 4 over 3. I think if you have maybe not really good for simplifying algebraic equations, I think you could just check the number. I think you should be okay. Should be the same conclusions. Okay, any questions so far? Okay, last subtopics before we end the class. Okay, I will give you some introductory for the some testing for convergences or divergences. And maybe some suggestion or tips, aside finding maybe another materials through some websites or perhaps YouTube. I think YouTube has a lot of content. You could also try using, I'm not sure if the free version of AI tools could help you to learn. Because I tried the paid one. So I tried. So I give the prompt that student and teacher, so that he will give me questions, and then also the solutions, and then I will adjust all the question and answer, and also check, because I think the paid version it has the additional tools for computations. So it will activating the code. So it can give you the analytical tools in Python, or I think in Python, and also if you are using the Wolfram Alpha, you can also connect to Wolfram Alpha to give you the resource. So you can check, like, give forward and backwards, and then you can take notes and write something, and you need to give prompt that it is actually works. But I think it is going to work for fundamental concept like calculus, maybe all the basic concept in science. It will work. If you give more, maybe more updated technology or trends, it seems that he will get hallucinated. Yeah, hallucinated. The AI will feel that he's thinking like weird and strange. So yeah, I think that's one way to learn. I also learned some tools from that part. So you can also, like, when I prepared some of the materials, I also test through that tools to see whether it can compute or not. Okay, anyway, so let's move on. So I forgot, I cut this. Show that the harmonic series is divergent. Okay, now we call this 1 over n is the harmonic series. You will see this harmonic series a lot in this chapter, okay, because this will be, I think, one of the foundations to compute the. Do you remember last semester in Calculus 1 we learned about the 1 over x and 1 over x squared. Okay? We call the unique integral at the end, right? Yeah, improper integral. So we learn about that. So this is also related. So we are going to see why this is going to be diverged. As in the improper integral, we see that this is also diverged, right? But now we see in the harmonic series. If we see this as a sequence, 1 over n, this is converged, right? It converges to 0. But if we add all those numbers, it says it's diverged. So let's see what we can do for this one. So, in this particular example, I will consider, so I will not consider all the other partials. So I will only consider the partial sums that start with the S2, S4, S8, S16, S32, and so forth. So all the multiplication of 2, okay? All these S, okay? So why? Because this will be simplified in our computation, and we could see the proof immediately. Okay? It doesn't mean we throw away the S1 and other S, but we could see from this part that this will be true. So the S2 is 1 plus 1 over 2, right? And S4 is 1 plus 1 over 2 plus, let me write with a parenthesis, 1 over 3 plus 1 over 4. Which this is going to be larger. For sure, this will be larger than if we change 1 over 3 with 1 over 4. Okay, so for sure this will be larger than this one. So I will just compare with some easy number that is easy to compute. That's why we took only S2, S4, S8, and etc. Because we are going to see the whole number when we combine. Okay? Since this is going to be half, right? So we could say that this will be equal to 1 plus 2 over 2, or 2, right? Now the same way, we take the S8. Now S8, we have 1 plus 1 over 2 plus, we have all this, and we have 1 over 5, 1 over 6, 1 over 7, 1 over 8. So this parenthesis is telling you that this is going to close to 1 over 2. And this will be going to close to another 1 over 2. Okay? And this will be greater. So now we change all the 5, 6, 7 with 8 and 3 with 4. So we are going to see a good number here. 1 plus 1 over 2 plus, this will be 1 over 4 plus 1 over 4 plus, this is going to be 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8. So this will be equal to, so this is half, 1 plus 2 over 2 plus 1 over 2, so 3 over 2. Notice that when we have the S16, since this is the multiplication of 2, the power of 2, so we are expecting that the next term will have 1 plus 4 over 2. Okay? So we are going to have, aside from this, The 16 will have 1 over 16, 1 over 16, 1 over 16, while in this part, we still have 1 over 9, 10 until 16, okay? So this means that every time we increase the n, it will always, the left part, is always greater than this. And this is going to increase forever. As we increase the n, this will increase forever. It means that it is not going to stop. Okay? It's not going to stop. So we are going to see that this is going to increase forever. And we can conclude that this harmonic series will always be divergent. Okay? It's always be divergent. We could say it here that let me just write a simplification that this will always be 1 plus 4 over 2, and S32 is always greater than 5 over 2, and so on and so forth. And in general, the S with 2 with power of n is always greater than 1 plus n over 2. It shows that when S2 with power of n is going infinity, then the sequence Sn will be or is divergent. So the harmonic series always divergent. Now to end today's lecture, I will give you these two statements, and we are going to see this statement practically. Okay, since we know whether the series is convergent or divergent at the beginning, like for some test or for some like the harmonic series or maybe geometric series, so we know whether it's convergent or divergent. Then one theorem, I think we can discuss this theorem next week. The series is, if the series is convergent, okay, it says if the series is convergent, the limit of the sequence is 0. Okay? But I hope you don't make mistake. It doesn't work if you reverse. It doesn't work. It doesn't work. So if limit is 0, it doesn't mean, it's not the same that this will be converged. So let me write as a notes here, and we can discuss later. So if the limit is 0, it's not necessarily means that it is convergent. It could be diverged. But if you know the series is converged, then you can take the limit as 0. Then we arrive at the first test for our convergence divergence. If limit doesn't exist, okay, or limit is not 0, okay, now it's not 0, then the series will be divergent. Okay. So at the beginning, if you check the limit of the sequence doesn't exist and the limit is not 0, this will be divergent. This will be divergent. Now if we check the harmonic series 1 over n, it is 0, but it's divergent. It's not convergent. So it doesn't work if we reverse the first statement. Okay. But for the test for divergence, if we can find the limit, if it doesn't exist, this is not 0, then it will be divergent. So this is the very first test that we can check. So every time you see the series, you can take the limit. If the limit doesn't exist, if the limit is not 0, you can just answer, okay, it's divergent. It's divergent directly. And for other tests, this first test will be always at the beginning. Okay? So there will be some tests and methods, but the test for divergence will always be your first choice to check. Okay? Okay, I think we are going to end up until here. Okay. So next week maybe some of the example and exercise, and also exercise for your quiz. Okay. Do you learn factors in physics? I mean, the whole thing, or dot product, cross product, right? Or no? Cross, no?
We're learning
The product. How about cross? No? Oh, okay. Okay, I think we finished.